Dipanjan as his co-guide from IIT Bhubaneswar. So he mostly works on Indian Ocean warming and how it impacts the monsoon rainfall. So he's looking into the intensification of the rainfall over Northwest India. So he has some good results. So let us see what he has done for his PhD. Thank you.
Good morning, all. Is it working? Yeah. Good morning, all. First of all, I would like to thank Ananthika for giving me this opportunity to present my result here at IITM. As Ananthika introduced, I am Ligin Joseph, a first-year PhD student at the University of Southampton. Today, I will be discussing about the increased summer monsoon rainfall over Northwest India. And I would like to take your next 20 to 25 minutes to convince you that this increase in the precipitation is caused by the Hadley cell expansion and the Indian Ocean warming. So these are my co-authors, Dipanjan Dev from IIT Bhubaneswar, who is here, Nicholas Fils and Robert March from the University of Southampton, and Joel Hirshi from the National Oceanography Center, Southampton. Yeah. So as we all know, India receives most of its rainfall during the Indian summer monsoon season, which spans from June to September. During this season, the southwesterly wind carries moisture from the ocean towards the Indian landmass, resulting in rainfall. The figure here shows the Indian summer monsoon precipitation trend during the 1979 to 2022 time period using the IMD daily dataset. The positive trends are plotted here in blue, the negative trends are plotted in red, and the hashes signifies a region where the trends are statistically significant. Over the Northwest India, we see significant decrease in rainfall. This phenomena is very well addressed in the existing literature. But the story is different over the Northwest India, where we see significant increase in rainfall. What's remarkable is the Northwest India, despite being a semi-arid region, does not conform to the usual wet gets wetter, dry gets drier narrative. This sparked our curiosity and led us to delve deeper. Therefore, the aim of our study are thus to unreveal the underlying physical mechanism driving this increased precipitation over the Northwest Indian region. So before diving into our findings, it is necessary to look at some of the relevant previous research in this field. For example, a research from P.V. Rajesh and B.N. Goswami titled Climate Change and Potential Demise of the Indian Desert showed that the Indian summer monsoon is expanding westward. And this expansion is a result of the westward expansion of the summertime ITCZ, which is driven by the westward expansion of the Indian Ocean warm pool. And another study from Lee et al., which was published in November last year, they showed that the Middle East warming in the spring enhances the rainfall over Pakistan. They showed that the springtime warming in the Middle East result in decrease in the pressure over that region, which increases the pressure gradient between the ocean and the land, which shifts the lower level jets northward, resulting in increased rainfall over the Pakistan and Northwest Indian region. And another study from Ramesh Kumar Yadav titled The Recent Trends in the Indian Summer Monsoon Rainfall showed that the ISMR trend is associated with the south central equatorial Indian Ocean warming. They found high correlation between the geopotential height at 200 hectopascal and the precipitation, especially over the west and south of India. Now, based on these studies, it is clear that the Indian summer monsoon rainfall is increasing over northwest India. However, the impact or the effect of the large-scale wind circulation changes still remains unexplored. Therefore, in our study, therefore the aim of our study are thus to investigate the increasing precipitation over northwest India using the observational and reanalysis dataset, and especially focusing on the role played by the large-scale wind circulation changes. These are the datasets we used. For precipitation, we used the IMD daily dataset. For the atmospheric variables like wind, specific humidity, and vertically integrated water vapor flux, we used the ERA5 monthly data. We used the Hadley SST, and we did our analysis for the 1979 to 2022 time period. Now, focusing over the northwest Indian region, we observed a precipitation increase of 40%, while the evaporation has increased only by 10%. This suggests that the moisture is coming from some external source. So to investigate this further, we computed the vertically integrated moisture transport budget, and the mean of the moisture transport is plotted and shown here in blue. The mean suggests that usually the moisture enters from the southern and the western boundary and exits to the eastern and northern boundary. Then we plotted its trend here in red, and the trend suggests that more moisture is entering from the southern boundary and less going out through the eastern and the northern boundary, creating an overall moisture convergence along this region, which can enhance the rainfall. Then we computed the vertically integrated moisture transport trend, and it is shown here. Here, the positive trends are plotted here in red, and negative trends are plotted in blue. And this will be the case of the case for the rest of the trend plots. And the arrows are plotted only if one of the component of moisture transport is statistically significant. And by vertically integrated moisture transport, I mean moisture transport integrated throughout the atmosphere column. Now, this trend shows that there is an increase in the moisture transport along the cross-equatorial monsoon winds pathway, which originates from the Pacific and South Indian Ocean. And from the literature, we know that 90% of the moisture in the atmosphere is situated at lower levels, at levels lower than 500 hectopascal. And usually for the monsoon circulation, we use the 850 hectopascal level. So we computed the moisture transport at 850 hectopascal, and its trend is shown here. Now, these two plots resembles very well with each other, suggesting that it is the moisture transport at 850 hectopascal which drives the vertically integrated moisture transport. Now, to individually access the contribution from the specific humidity and wind speed towards the moisture transport, we use this decomposition method. Here, Q bar and U bar stands for the mean of specific humidity and wind speed. And the first term here signifies the contribution from the change in the wind speed to the moisture transport, which is plotted here. And the second term signifies the contribution from the change in the specific humidity to the moisture transport trend, which is plotted here in the lower panel. And comparing these figures, it is evident that the moisture transport is dominantly driven by the winds, but we can see minor but significant contribution from the changes for the specific humidity, especially along the Arabian Sea and west coast of India, where the changes from the specific changes from the wind speed are insignificant. Now, since winds are really important, we look at the 850 hectopascal wind trends, which are shown here. And we can see an anticyclonic motion around the Southeast Pacific, which extends and enters towards the Indian Ocean region. And we can also see winds coming from the South Indian Ocean and merges and strengthens the cross-equatorial monsoon winds. Now, these winds can impact the evaporation as well. So to better understand that, we plotted the evaporation trend, which is shown here. Here, we can see an increase in evaporation over the cross-equatorial monsoon pathway. And this is the same path where we see an increase in the wind speed. This suggests that an increase in the wind speed increases the evaporation, which can potentially increase the moisture transport. Now, the next question is, what drives these large-scale changes in the wind pattern? And we all know winds are mostly driven by the pressure gradients. So we then computed the trends in the mean sea level pressure, which is shown here. The mean are plotted here as contours. We noticed an pressure decrease over the Indian Ocean and an increase in the pressure over the Southeast Pacific. And this creates a zonal and meridional Southeast Pacific. We can see an increase in the MSLP over South and the South Pacific and South Indian Ocean as well. This creates a zonal and meridional pressure gradients. Now, to understand its impact on the wind circulation, we plotted the wind trends on top of the mean sea level pressure trend, which are shown here. Here, we see along the Southeast Pacific, an anticyclonic motion is created around the increased pressure, which extends towards the Indian Ocean region because of the low pressure situated over the Indian Ocean. And winds from the South Indian Ocean also merges towards the monsoon flow, and this strengthens the cross-equatorial monsoon flow, which brings more moisture from the ocean towards the Indian landmass. Now, the next question is, what drives this mean sea level pressure trends? And mostly the pressure trends are driven by the temperature and also the ascending and descending motions in the atmosphere. And over the Indian Ocean, we can see that we all know that Indian Ocean is warming rapidly. And this warming can explain the decrease of pressure over this region. But what about the increase of pressure in the Southeast Pacific or South Indian Ocean? Now, if we look at this increase in pressure, this is situated between 20 south and 40 south. This is the region where the subsiding branch of the Hadley cell is situated. And also, if we look at the mean sea level pressure trends here, with the mean plotted as the contours, we can see that the high pressure has been shifted southward or poleward. And this suggests that there might be some effect from the Hadley cell extent, which affects the sea level pressure. And we then looked at the literature and found this study from Daniel and Kevin, the response of local precipitation and sea level pressure to Hadley cell expansion, where they used the ERA interim dataset from 1980 to 2020, and they computed the sea level pressure trend, which is shown here. This trend matches very well with the pressure trends that we have, even though the dataset and the time periods are different. So then what they did is they computed the Hadley cell extent as the latitude at which the mean meridional stream function crosses zero poleward of its tropical extremum. And they regressed this Hadley cell extent onto the mean sea level pressure, which is shown here. And they found high regression coefficient between these two parameters, especially along the South Pacific and the South Indian Ocean, suggesting that the Hadley cell is impacting the sea level pressure. Now, it is well known in the literature that the ENSO events affect this Hadley cell extent. Therefore, they remove the ENSO effect from the MSLP and again regress the ENSO remove MSLP on the Hadley cell extent, which is shown here. And they still found high regression coefficient over the South Pacific and the South Indian Ocean. And this suggests that the Hadley cell has some impact on the sea level pressure. Now, there are different studies which show that the Hadley cell is extending. For example, this study from Sheehan et al., they reviewed different mechanisms which are responsible for this Hadley cell expansion. For example, they showed that the increase in greenhouse gases warms the troposphere and cools the stratosphere. This can result in increase of tropopause height, which can further expand the Hadley cell. And there are other different mechanisms they discuss as well. Another study from Kevin et al., they use the CESM models to look at the Hadley cell extent in the past and for the future. For example, here they show the time series of the Hadley cell extent, and this is for the northern hemisphere. On the y-axis, we have degree north, and on the x-axis, we have years from 1920 to 2100. And here we can see that the Hadley cell is expanding poleward in the northern hemisphere. And here they did the same analysis, but for the southern hemisphere. And on the y-axis, now we have degree south. And we can see that the Hadley cell is expanding poleward here in the southern hemisphere as well. Now, to better understand the Hadley cell extent contribution to the mean sea level pressure trend in JJAS, we did some same analysis as did by Kevin. So here we computed the Hadley cell extent as the latitude at which the zonal mean of the zonal wind at 925 hectopascal is closest to zero. Then in the literature, it is well known that the Hadley cell expands during La Nina and contracts during El Nino. So we had to remove the ENSO effect from the sea level pressure and other parameters. So here we use this method to remove the ENSO effect. Here, A of x, t is the observed field. In our case, it is the MSLP. And N of t is the Nino 3.4 time series. And R of x is the slope of the linear regression between the Nino and the observed field. In our case, it's MSLP. And we regress that Hadley cell extent onto the mean sea level pressure, which is shown here. We also found high regression coefficient over the Southeast Pacific and South Pacific and the Indian Ocean. And this suggests that the MSLP over this region is attributed to the poleward shift and expansion of the Hadley cell. Now, other than this, the temperature can also impact the pressure. So we looked at the SST trends, which is shown here. And the SST, we see significant cooling of SST along the Southeast Pacific, which can be attributed to the latent heat loss and Ekman pumping caused by the wind trends over this region. And this cooling can further enhance the sea level pressure, therefore acting as a positive feedback in the system. Now, to summarize, we found that the pressure over Southeast Pacific is increasing due to Hadley cell expansion. And this creates an anticyclonic motion around the high pressure, which extends towards the Indian Ocean region because of the low pressure situated over this region. And because of the meridional pressure gradient, we see winds from the South Indian Ocean also merging towards the cross-equatorial monsoon flow, which strengthens this cross-equatorial winds and brings more moisture from the ocean towards the Indian landmass, which results in a 40% increase of rainfall over this region. Also, another striking feature here is this low pressure is situated partially in the northern and partially in the southern hemisphere. So, yeah, I have to go back. Yeah, so a cyclonic motion is created along this low pressure in the Indian Ocean in the southern hemisphere, which when enters the northern hemisphere is shifted towards the Indian landmass because of the change in the Coriolis deflection. So this results in more moisture being transferred from the ocean towards the Indian landmass, resulting in increased rainfall. And thank you for listening. I'm happy to take any questions that you might have.
Thank you, Ligin. So very nice talk, simple way of explaining how the Pacific is impacting our northwest monsoon, increase in precipitation. I have one question. So have you linked it to low pressure systems, like whether we are having this moisture transport is impacting the low pressure, the westward propagation of the low pressure? That might have an impact. Yeah. So do we have questions from the audience?
Yeah, thank you, Ligin, for the nice talk. I was wondering, like, what is the period you have taken to compute the trends and all?
It's from 1979 to 2022.
Yeah, because the SSTs and all, whatever trends you have shown, it is shown like a mean picture looks like an La Nina-like situation in the Pacific, and Indian Ocean, it is like a negative IOD type pattern, like warming in the east and cooling like that. So is that the signal coming out for the longer period?
So this is really a good question, and we have looked into it as well. So this is the trend with ENSO, but if we remove the ENSO effect, like using the method that I showed before, we still see this trend. So this suggests that it might be independent of ENSO events.
Thank you. That's
all. It's a really nice talk. I enjoyed your talk. What Ayantika also said, I have a similar comment. In recent studies by the Hunt et al., they showed that some of the lows and depression, they are really long lasting and they travel deep into the northwestern region, and they showed that there is a strong contribution from such systems. So that would be also another topic, because you also said specifically that there is a 40% increase.
Yeah, thank you for pointing out. We have not looked into it, but we are really interested.
Okay.
Maybe the person can answer.
Yes. So it's a good question. The thing is that when you look into this northwestern of India, so the wind drives because of the pressure gradient, correct? So you have the shifting of the masculinous high poleward, but you also, as you said, is depressions, low pressures that are a system that attracts the moisture and the wind. So it's all, I think, included in that cross equatorial flow. So if you have a depression, but if you think about local, not probably attracting water mass from the Indian Ocean, if you think just by local in situ, it might have absolutely, it might have an effect. And if you want to quantify, if you look into the budget that Ligin showed, that you see that 40% increase in precipitation, but only 10% increase in evaporation. So it might have contributed, but not that much. So, but if you want to really quantify, then you have to use some kind of trajectories to understand that if it's really local or it is coming from somewhere else. Yeah, thank you.
Yeah, interesting talk. I just want to ask you whether you have quantified the Hadley cell expansion. Are you telling it as intensification or expansion?
Both. It's expanding and intensifying.
But I didn't find any estimate for that. You didn't give me the extension of the 1 degree or maybe 0.4 degree. What is the estimate for that?
Yeah, I didn't show that type series here, but I have that with me, and maybe we can discuss that later as well. Also, there are different studies which show this extensions. So here, like here, they use different models, but they show like the southern hemisphere minus 32 till 33, 34, something like that.
But this will be global mean.
Yeah, global.
But what we are talking about is regional Hadley cell, local Hadley cell. It's totally different from the global mean, which is only occurring at the Indian region. It's a reverse Hadley cell. So are you talking about reverse Hadley cell or the global mean?
Like we are talking both about the Hadley cell expansion in the Indian as well as the Southeast Pacific. So we took that into account. We also took the global mean.
Okay, you are talking about both picture.
Yeah, both.
Over the Indian Ocean, over the, where it is reverse Hadley cell.
Yeah.
And also over the okay, but I didn't find any estimate for that.
Okay, yeah, I have not included that in my presentation.
And then what is the relation between the MSLP and Hadley cell you were talking about in some?
So in my view, what it is like, Hadley cell subsiding branch can increase the pressure over that region. Like if it is subsiding, more subsidence is there, which can potentially increase the pressure over that region. It's like opposite to the SST.
It can be on the other way around also, right? Because of the strong anticyclone, you can have a strengthened Hadley cell also, right?
Maybe it depends on that.
So yes and no. The thing is that when you look into the main picture, can you go to the main picture? So the contour, yes. So this one. So the contour here is your main field. But when you see the trend and you see it's kind of the red contour on the southeastern Pacific, that it's shifted kind of southward. the question, and when you see in the Indian Ocean also, the mean, and you see the core, it's kind of shifting southward. When you think about it, yes, it is important that what you have talked about. But I think when you show the time series of how they have calculated how we have calculated the Hadley cell extent, that might, I think, explains your query on that matter.
So there is a shift for the subtropical anticyclone over the south,
Yes.
so towards south, and
Yes.
then you claim that there is a shift of the north of the reverse Hadley cell to the north over the Indian Ocean, right?
What we talked about is, if you look into the shifting of the Hadley cell in the southeastern Pacific. So when you shift, so when you have a high pressure, we know that because of the Coriolis, you have this in the southern hemisphere, you have an anti-clockwise circulations. Correct. So when you have an anti-clockwise circulation along the coast of the Southern America, you increase your Ekman transport because it will be to the left, and that's what he showed, the SST cooling down. So it also reinforces to the high pressure to the there, because if the SST would be warmer, you would expect a low pressure there. So I think when we talk about that, if it's anticyclonic first and the high pressure after, or the high pressure first, it's a chicken and egg problem.
My question is, there is a southward expansion of the MSLP, maybe anticyclone, over the Indian Ocean, okay, to the south. So that means the masculine high over that is expanding towards south. So, but you say that the Hadley cell, which is a part of it, it is expanding northward. So how it is possible? That is the point I'm getting confused.
I don't think
the thing is that the shading part, which
Yes.
is shown,
Yes.
is the trend,
yes.
and the contour is the climate, right?
Yes.
Okay. So related to climatology, you have a shift for the Hadley cell, shift for the what is that, masculine height towards south.
Yes.
And then you also say that there is a shift of the Hadley cell to the north. That means the reverse Hadley cell to the north. Is it correct?
No.
Hadley cell over the Indian Ocean region, but the westerly branch, which is coming out from the enhanced subtropical high over the Pacific, is in turn pumping more moisture into northwest India. Is their point, I guess.
Yeah, that's
Hadley cell already mentioned.
But no, but they're not mentioning reverse.
Yeah, they are not
over the.
Okay. Yes. Okay. Yeah. Nice talk. Nice.
Nice talk, Ligin. But did you verify this for like case study 2022 monsoon 2023? For that also, like northwest was more positive and east was negative. So for 2022 and 2023, did you check that for any?
No, we didn't check that individually, but it's a good point. Maybe I will look into it.
Yeah.
Yeah.
Okay.
Thank you for pointing this out.
Any more questions?
Just one clarification. Nice talk. So you mentioned La Nina expands the Hadley cell, right?
Yeah.
So is there a need to eliminate the La Nina years as well as you are doing for El Nino?
We are doing that for both. We are taking the Nino 3.4 time series, which includes both La Nina and El Nino.
Okay, so you're
which we are eliminating that. Thank you.
So let us thank Ligin for a nice talk.
Thank you.
Thank you.
So much.
And there is tea outside.